So this is the basis of our analysis that follows. It is that the compositions, the bijections form, or they create an equivalence relation on sets. Okay, so that's what we care about right now the most. So an equivalence relation on sets. Okay, so then, okay, so we set it aside and we're going to use it later. Right now we are then thinking in terms of, well, the what I'm referring to here is this statement. Where is it? Yeah, relations. The word equivalence the concept equivalence relation has the word relation in it. Is it a coincidence? No, it's not, because equivalence relation is a relation. Okay, so let me clarify that. So, so as you can see, every relation is simply a subset of the of a Cartesian product of x and y. Okay, so you can say that it is a relation from x to y if once again there is a subset G of that Cartesian product, just like that picture on the left, x and y, and then you say that if you have x here, then whatever we cross here, that these values are related to x. So these are related to x, this particular value of x. Okay, so then it only becomes natural to ask what about equivalence relations. So equivalence relations are special kinds of relations. First of all, what's so special about it? They're relation from x to x. Okay, but you can see how it works out, that there might be many values for each x illustrated by that little picture, and then whatever value of y you have there, they will be that x and that y will be related. Okay, so in other words, x is equivalent to y if xy belongs to that set G in x cross y. Okay, so that's the idea, and that we can illustrate it with if we pick a few equivalence relations from before and illustrate them with their graphs. Okay, so for example, even numbers, even equivalent to even, and odd to odd. Okay, so what does it mean? Let's plot the graph of this equivalence relation. Well, so what we do, then my set x is the integers. Okay, so I put my integers on the x-axis and on the y-axis. Once again, it's from x to x. Okay, and then I plot the integers like this. Oh, in fact, I could probably alternate. So odd number, so say these are even numbers, and here also even numbers. Okay, and then these are odd numbers. Okay, so that is the relation. You know that odd will correspond to odd, even to even, but every odd corresponds to every odd, and same for even. So which means that my graph will look like this. Well, all of these are the elements of my graph. That's not right. Let me start over. Okay, so this is okay. As you can see, what I'm saying here, I plotted these orange dots to indicate that, for example, 1 is equivalent to 1 naturally, but it's also equivalent to 3. Okay, and 3 is equivalent to 3, and 5 is equivalent to 3. Okay, so that's why all of these points have to be there. but then also 0 is equivalent to 2 and to 4, and that's why we have these points. And then 2 is equivalent to 2 and to 4. Okay, and then 4 is equivalent to 2 and 4. Okay, so this is the graph of the equivalence relation of odd versus odd and even. Okay, so all of these points are so as you can see, if you look at the straight line through say 2, and you see a bunch of numbers corresponding to, on the y-axis, they correspond to the even numbers. Okay, and every single one of them, so including -2. And if you start with odd numbers, then once again you have these points that correspond to say -1 over here. Okay, and this one and that one. I'm afraid I have to correct myself again. Like this. Okay, that's better. Okay, so if you just read these dots, you'll see exactly that. You read 1 equivalent to 1, 2 equivalent to 4, 4 equivalent to 6, and so on. 1 is equivalent to -1, and so on. So just the point is that equivalence relations are worthwhile to study, because equivalences, relations are worthwhile to study because that's such an important thing as equivalence relations is in fact a relation. Yes.
Does that symbol get used to negate something too?
In the book, rather online homework, they use the same symbol to negate, unfortunately, for whatever reason.
That's very unfortunate.
It is. Considering that there is that symbol that you saw not on the last test, but maybe on the previous one, that symbol, which is certainly better. From the context, it should be clear, because equivalence is that tilde, or that wiggle over there, it is when it's put between two symbols, then it is equivalence relation. When in front of it, then from the context you should guess that it is a negation.
Yeah. Okay.
Yeah. Okay. So that's just one example, and you can try to plot graphs of any equivalence relation you can think of. So this is the divisibility by 2. So two numbers are equivalent to each other when they have the same remainder divided by 2. If you try to do it by 3, you can do just as well. I did that again, like this. Okay. So as you can see, what do we have here? We have straight lines at 45 degrees. You can go that way or this way, and they're at 45 degrees. If you start saying, I'll say divisibility by 3, then you can see that the pattern will be different. So that may be, so that the homework plot the graph of the relation x equivalent to y if and only if x is equal to y mod 3. Okay, so same divisibility. That's what it stands for. Okay, so so now we are using that equivalence relation on all sets, which is two sets are equivalent when there is a bijection between them, and use it to study sizes of sets. In particular, specifically now, it's too easy for finite set. We want to study infinite. So over here we started with the a finite set, and they're very easy. So this is a finite set, and then there is a kind of a one sample set that is a perfect example of a finite set. Say for one element, number 1 put in there, and that's your set. Or set is of 2 elements, 1 and 2, and so 1, 2, and 3 that has 3 elements. So there is nothing tricky about it. It is when we start studying infinite sets is things become complicated in terms of comparison. Okay, so also this is the symbol infinity. Probably makes sense to take another look at it for a moment and compare it to its meaning in calculus, which is what I did over there. So they are related. because the thing is that the infinity is not a number. So how do we approach infinity in calculus? So approach infinity in calculus, how? You approach it at its simplest, we approach it with a sequence. Okay? So like I said, if you have finitely many numbers, you are still infinitely far away from infinity. If you have a sequence, then you make infinitely many steps, such as all of these, and you will get there. Not eventually, but you will be approaching infinity. Okay? So then the answer becomes then, and then what is a sequence? A sequence has infinitely many elements. So that's the relation. We are talking about the issue of infinitely many elements, whether or not we're talking about sets. Do they or do they not have infinitely many elements? So sequence is, in fact, that's another way to look at sequences. It is a function an. Say it is a function f from the natural numbers to the reals. Okay, so for every natural number, or at least starting with some point, you could start with 0, start at 1, start at 2. Doesn't matter, but that is pretty much the same thing. Just for every natural number, there is a real number assigned to it. That gives you a sequence, the one that you studied in calculus 2. Okay, so indeed that is the best relation you can do here to establish a relation between the infinity in the calculus. It's about numbers and quantities, and then now we are switching to a different angle. We're speaking of the question of how many, or how much, if you prefer, of elements a set has. Okay, so then we know that we do know, we would like to say that explicitly, that z, the integers, has infinitely many elements. So has infinitely many elements. Okay, so how do we say that? How do we say that? How do we explain that? So what does it mean exactly? It means that there is no bijection from z to x where x is finite. Okay, so in other words, it's not equivalent in size to any finite set. Seems so obvious, and it doesn't really require explanation, but we do want to work this out very carefully and very rigorously. So we actually, to demonstrate that z is infinite, we would have to prove this. Okay, so we are not relying on our observations, but rather or common sense. Once you get to infinity, well, the common sense frequently doesn't work anymore. So and that's the number step number one towards infinity, is to demonstrate that integers or natural numbers have infinitely many elements, which means exactly this. And that's every time we're trying to prove something about the size of the set, we have to think in terms of bijections. So we want to demonstrate that there is no bijection from x to z or from z to x, where x is finite. So how do we prove it?
With a theorem.
Yes, theorem. Theorem. There is no bijection from z to x where x is a finite set. How do we prove it? When we're trying to prove something does not exist, how we do, what is the starting point?
The limit?
No.
Or-
Limit?
I mean, sorry, never mind. Counterexample?
Not counterexample. No, counterexample proves that the theorem is wrong, as stated. It's not a counterexample, but a contradiction. about contradiction. So you assume the opposite of what you're trying to prove and then arrive to a contradiction. That will prove the theory. Okay? So in other words, suppose, so prove by contradiction. So suppose f from z to x is a bijection and x is finite. Okay, then arrive to a contradiction. Okay, so as always, try to unravel or unwrap the definition. So x being finite has to be explained, and by explain means using the definition. So there is, once again, if f is finite, means that it has a bijection with some specific finite set. So there is a bijection g from x to, say, 1 through n, for some n. Okay, so a finite set, which means that there is some n, the number of elements in that set, and whatever that number is, large or small, it doesn't matter. There must be a bijection between that set x and the set of elements of numbers through 1 to n. So, okay, so the last two sentences put together, what do we get? F and G, F from Z to X, G from X to this set. So, what are we looking at? Two functions, consecutive. Each of which is a bijection. They are the Z and X are equivalent, and then X as and the last set are also equivalent, which means that indeed a Z and that set are equivalent. Okay, equivalent in size, that is. Equivalent in size. Specifically, we have a bijection. H, which is the composition of those two. So G, F follows G from Z to 1, N. Okay, so we make this specific so that set X, which might be somewhat mysterious, but really it's not. So we rather prove that there is something simpler, more specific, entirely specific, in fact, that there is no bijection from Z to that set from 1 to N. Okay, so how do we arrive to a contradiction here? So why do you see a contradiction here?
What did you say?
Do you see a contradiction in that last statement?
Well, yeah, you said that it has infinite amount of elements, and that has a finite amount of elements in that statement for Z.
Yes.
So that's not right.
We have to be more specific.
Okay.
We have to point out the contradiction. So
That's
Z,
the contradiction right there. Z's got a finite. I don't.
we have to do more than that. So Z is,
People.
well, how about we pick, so just to say that we don't want to go back into that common sense or intuition that we already sort of put behind us, and we want to be precise
Can you state a number value for n?
we don't know what n is, and it might be large.
Okay.
But the point is that no matter how large it is, we still run out of elements.
Right. So can you give an example of what n could be to prove that it's not infinite? I don't know.
Right. Yeah, so we do have to point out, to demonstrate that there is no bijection, or there is a contradiction, we have to point out an element in Z that would not have a counterpart in that set, whatever, call it Y. So can you think of a way? So this is what we're looking at. We're looking at, let's take a part of the Z, say 1, 2, 3, and on, and then we have our function to the set Y, which is 1, 2, 3, n, and then it ends. Okay, so the arrows might point in any direction. So somehow there is an arrow originating from each of them, and there is no other. There's only one arrow.
The inverse?
Okay, go on. It is a bijection, so there is an inverse. The inverse.
Take the inverse
Of H. So consider H inverse. From Y, that's set, to Z.
above the arrow, did you mean the H, or is that?
Above the, yeah, I meant H, thank you. Yes, I see my mistake.
And where did Y come from? Like,
Just a name for Z. I kept repeating the set from 1 to N, so I called it Y. But it's still a set from 1 to N.
oh, okay.
So we reverse the arrows, and that is helpful. Why is it more helpful? Because I might have reached N, and these elements, in fact, might pass. If we go from Z to Y, these all arrows might go somewhere outside. Well, they cannot go outside, but what I meant is the opposite. They might be like this. So, well, there is no pattern, I guess, what I'm saying here.
There's just elements that won't have an arrow. Right.
Yeah, we need to demonstrate that it's not possible to assign arrows between these two sets. This one continues on, and the other one does not. Okay, so this one ends. This is the whole thing is right here, and this one it keeps going like this. Okay, so if we reverse the arrows, then we can point out the element which does not have a counterpart. So here's how we can try it. So let M is the maximum of H inverse of X. X run from 1 to N. So we reverse the arrows. That's how many elements Y has. And so we reverse them all, and then plus 1 over here. Okay, so the claim is that there is no counterpart for M. Right? So once again, we reverse all the arrows, and it gives you a bunch of elements in here. Okay? This set then has at most n elements. So at the very least it is finite. If it is finite, maximum is defined. So you have finitely many numbers, you take a maximum of those. Okay? Add 1. So this number is certainly, that maximum is an integer, okay, and then you add 1, it's still an integer, and then ask yourself what is H of M. It cannot possibly have an arrow originating from it, because all the elements will go to, where do they go? Well, there are no arrow arriving to H, to M. Okay, so in other words, let me what is let me put it this way, then there is no x such that x and y such that h inverse of x is equal to m. Okay, so h of m is undefined. Okay, so that's a contradiction. Okay, so well, maybe we'll come back to that proof again later. Let's just continue on with things that are more visual, I suppose. And that is, so let's look at infinite sets. Both sets are infinite. That we can handle easier. So questions such as compare the sizes of the sets. These sets, even and odd. So, even numbers, odd numbers. Say this is x and this is y.
We mean compare the size.
The size, meaning in the sense that we have been talking about the cardinality of sets in terms of the bijection. Is there a bijection between them? So they have the same number of elements, or they have the same cardinality when there is a bijection between them. Okay, so is there a bijection between them?
They have the same number of sets.
Same number of what?
Same number of elements.
Well, that's what we were trying to demonstrate. That is how we understand it. What does it mean for a set to have two sets have the same number of elements? One and only one explanation is there is a bijection between them. Okay, so you cannot say they have the same number of elements unless you point out the bijection between them.
You can have a bijection when they go to infinity.
Well, there are infinitely many of them, but we already know how to handle infinite sets. A bijection.
What's it mean to have a bijection between two?
Yeah.
Well,
I mean, I know isn't it onto one-to-one, but I don't get what.
Between two
Yeah.
sets, I don't
Yeah,
really-
but yeah, I don't.
no, it's always been this way. Well, what else? Two sets. One set is all even numbers, the other set all odd numbers. Provide a bijection if you think they have the same number of elements.
Yeah, but what do you mean by provided bijection?
A formula. How about a formula?
Okay.
Okay. 2n. Go, where should it go? 2n, an even number.
2n plus 1?
2n plus 1. There you go. So that's my formula. That's my f. So certainly, as you can see on the left, this is 2n is definitely even. 2n plus 1 is definitely odd. Okay, so that works out. So you still have to demonstrate the rest of the things, such as we have to demonstrate that is a bijection, so it has to be one-to-one onto. So, okay, so first, it's onto. Show that it is onto for each odd x, find even y such that f of x is equal for f of y is equal to x. And it's one-to-one. Show that, so if y is not equal to y prime, then f of y is not equal to f of y prime. Okay, so another way to accomplish this is find the inverse. It's not a shortcut, but it is kind of makes your task more specific. Okay, so if f of 2n is equal to 2n plus 1, f inverse of 2n plus 1 is equal to 2n. Okay, there you go. So as you can see, you can plot it. It's really not hard if you just put all even numbers on the x-axis, and you put all the odd numbers on the y-axis, like this. Then, as you can see, all we do is we just shift. So we add 1. If you start with an odd number and you, start with an even number, add 1, you'll have an odd number. So, for example, where does 0 go? It goes to 1. So that's a point here. 2 goes to 3 here. 4, so 0, 1, 2, 3. It's not 0, 1, 2, 3, but 2, 4, 6. And these are 1, 3, negative 1, negative 3. Okay? So I'm building a graph of my bijection. So as I said, 1 goes to, 0 goes to 1. That's the first circle. The second one, 2 goes to 3. Okay? 4 goes to 5. Okay? So it's here somewhere. And then you can have more. Negative 2 goes to negative 1. Okay, so that those green circles, this is the graph of my bijection, and everything applies to the vertical line test. There's exactly one value for each x. The horizontal line test, there's exactly one x for each y. Okay, so that demonstrates graphically that this is a bijection. So you can actually rewrite this thing better. So this is a little bit awkward, this. So you can just write f of x is equal to x plus 1 for an even x. Okay, and then f inverse of y is equal to y minus 1 for an odd y. Okay, so that is much more specific. The formulas become very, very simple, right? Very explicit. So it is well defined, defined for each y, it is defined for each x. Adding 1, then subtracting 1, so you need to demonstrate that this is indeed the inverse. How? Well, you take the composition, think about it. The composition, adding 1, subtracting 1, yeah?
Is the second equation always true? Like, y is 1?
Y minus 1, whatever y is, I can subtract 1, right? So,
Because y is always odd? Is that what you-
y is odd, yes.
Okay.
So when y is odd, y minus 1 is even.
for
But that doesn't
y,
produce
yeah.
a even number, right? So
Odd minus 1 is even.
1 minus.
Odd minus 1 is even. And on the other hand, that's the second line. The first line, even plus 1 is odd. Okay, and then as you can see, they will cancel each other as they are inverses. If you take the composition of f inverse f of x, what do you have? You first add 1, then subtract 1. So it's going to be x. So it is definitely the inverse, and conversely, f of f inverse of y is equal to y. So they are indeed inverses of each other, and so we have demonstrated that there is a bijection between these two sets. We certainly guessed early on that they have the same magnitude, the same number of elements, and we have proven now by specifying a formula for the bijection. So it is not going to always be as easy, but it is certainly is a starting point, and that's the standard by which we're going to judge our proofs. So even when the answer is obvious, we want to demonstrate that we want to prove it, not just relying on our common sense. And to show why when common sense fails is here's fails when infinity is involved. Here's another example. So the question is the same. Compare the two sets. Even and z. Which one? Well, what is how compare the sizes, not the sizes of the sets. So all even numbers versus all integers.
Integers are twice as big?
What?
Integers are twice as big?
Yeah, that seems like. That's what common sense tells you. Right, because you take all even numbers, right? Then we know that the numbers, the number of odd numbers is exactly the same. We just demonstrated. We put them together, and we get integers, right? So this is even, union, odd, right? So then it sounds like Z has twice as many elements.
But they both have infinitely many.
Well, exactly. So if you multiply infinity by 2, what do you get?
Infinity.
Infinity, which is that a different kind of infinity, or is it's the same infinity? Okay, so if it is if that is clear, then all we need to do is to demonstrate that is indeed our developed intuition is true.
So it's just reaching infinity slower, but it's still going to infinity?
No, we are not reaching it. That's not calculus. So when we're not trying to
Yeah.
approach infinity, we are looking at these two sets as if they exist, and we have holding them in two hands, and we're trying to compare them.
Okay.
So even though there is clearly Z is bigger, has literally more elements, literally has extra elements. So extra elements than the even numbers. The magnitude is the same. The cardinality is the same. So all we have to do is to find bijection. So this time it is much less obvious or predictable that such a bijection exists, and that's why that example was important, because we know what is that we are expecting to have. We want to have a specific formula. So a formula, a bijection, f, from even numbers to z. 1 to 1 on.
2n and n?
That's right. F of 2n is equal to n. More precisely, that is the idea. I prefer more precise writing. It is f of x is equal to simply x over 2 for each even x. Okay, so if x is even, then x over 2 will be an integer, and so we're okay. Once you write it this way, then you can easily think of the inverse. What's the inverse? There is no trick. What? 2x. 2y. Okay, so once again, for each integer y, okay, so once again, the formulas are so simple, and in fact they're applicable to any real number. So if these two functions are inverses for each other for real numbers, that certainly they remain to be inverse whenever we only limit ourselves to integers. And the only thing to watch out for is that it does work out. So we have to demonstrate, as we already have, that whatever if you plug in an even number, the output of f will be an integer. Naturally it is. Divide by 2, still an integer. And conversely, if you start with an integer, y, you multiply it by 2 to get an even number. Of course you do. Right? So indeed, it is both of the functions are well defined, and they are inverses of each other, so which proves that what we have is a bijection.
How is it onto the if?
Well, because the inverse is defined for every y, right? Which makes f onto.
But there's twice as many elements, right?
Right. So that's the part that we have to get over, the common sense. Get over it. So whenever infinity is involved, the common sense might fail. So a bigger set has exactly as many elements. And once you start down that road, you can certainly think of many other similar ideas. What about? Oh, well, by the way, this is how we write it. Even z. Okay, so remember, vertical lines indicate the cardinality. Of the set. What about odd numbers? Odd bijection. Well, why the number of odd is the same? Because we already know in the previous example we have established that odd has the same cardinality as even. So last example. And the even have the same cardinality as z, so then odd has the same cardinality as z, because it is an equivalence relation. So we don't have to create a new bijection, right? So because we better it's such a good thing is equivalence relations that it is better to be used. It saves you a lot of work. So once you demonstrate that pairwise, I'm using transitivity. So this is the transitivity. Transitivity of this equivalence relation. And so odd is equivalent to even equivalent to z, means that odd is equivalent to z. Okay, and then you can think of many other. Can you suggest down this road what else set have the same cardinality as z amongst the integers? How about divisible by 3? So divisible by 2, that's what we just did, that's even numbers, right? And then divisible by 3, so can you think of a bijection? F of x is equal to what? X over 3. So similar. Okay, and then if it is numbers that are not divisible, but rather the ones that really have a remainder 1 of under division by 3, once again the same number.
They get what number?
Say same number of elements as z. So, hence the definition. A set with x with the cardinality of z. So x is z, same size, is called countable or infinitely countable. So infinitely countable sometimes is added in order to discard the finite sets from this. So countable, a bunch of sets are countable, divisible by 3, divisible, not divisible by 3, divisible by 2, divisible by any number. All of these numbers are countable. What about prime numbers? What?
Didn't you talk about the remainder of 1 though?
Well, no, the prime numbers, there are fewer prime numbers in the sense that then they're all odd, except for 2, and then there are fewer of them than odd numbers, because some of the odd numbers are not odd, are not prime. So, but you still want to try to demonstrate that primes are countable. They're actually the harder part that, not the harder part, but at least this extra thinking required is to demonstrate that there are infinitely many of them.
This is countable?
Countable, yes, that's the definition, countable. So you can count it, even though it takes infinitely many steps, you count them. If you have infinitely long time available, then you will count them all. And so that's called countable. So prime numbers are countable, infinitely countable, if you demonstrate that there are infinitely many of them in the first place. Anybody knows how to prove that there are infinitely many primes? So when you know that there are infinitely many of them to begin with, then you demonstrate that they're countable. Okay, so that is countable sets are interesting, but they're not all sets are countable. So are all sets, all infinite sets countable? The answer is no. So there are bigger sets. There are bigger sets than countable.
It's like all real.
That's right. So answer number 1 is the reals. Okay, so we'll demonstrate that
Why is that countable?
it's not countable.
Because why is that not countable, but all integers are?
Right.
That's crazy.
Don't all reals technically go to infinity?
You still think in calculus. You're thinking about that infinity, which is far a point that locate infinity far away from where we are. We are counting the number of points, and can you count the number of reals? And the answer is no. But then it takes some proof. Okay, so let me. Well, it is quite tricky. The proof quite tricky. So let's do it next time. But let's look at the other not countable sets. What are sets are equivalent to R? And the answer is, for example, example from calculus is I'll put my reals here. And I'll take a small interval. How about between negative pi over 2 and pi over 2? And I put a function here, which should be familiar to you. Does it look familiar? It is the tangent, that's right. Y is equal to tangent x. And tangent creates a bijection between, so f from what? That interval, negative pi over 2, pi over 2, to the reals. If you look at it carefully, it is a bijection, so it satisfies the vertical line test, horizontal line test, so it is indeed a bijection, so that small interval has as many elements as the whole real line. Okay, so you can certainly think of many examples like that, and we will, but it is really interesting. This is a really interesting part about why it's not countable.
That's,
Okay,
that's
yeah.
not countable, but like y equals 2x is countable? said
You mean the even numbers are countable, yes.
But why? So what's the difference?
The difference is there is no gap. This is very thin and sparse, and this real numbers is, how do you say, you can infinitely divide it into smaller and smaller pieces, which is really not the real reason, but still, best I have right now.